Okay, let's talk about entropy. Before we talk about entropy, let's recap what we had talked about the second law of thermo. Second law of thermo. And you might think that today's class has absolutely nothing to do with the midterm, which is true in a sense. I won't be asking you anything about entropy, but the procedure, the framework, the way of thinking that we have in today's class, if you're comfortable with it, you will be comfortable in the midterm. The same thing, du, dq, dw type things. So second law of thermo, we had three statements. One of them was Kelvin, one of them was Clausius, and the third one, I don't know, we can call it Marco. You okay with that? Okay, great. It doesn't have a name, so we can call it Marco's statement henceforth. Good job.
No,
Oh, you are Marco, and you are, wait, Rob. Bob. No, Rob, what's your name? Andrew, sorry, this is so embarrassing. Does anyone know my name? If you miss it, I'm sorry, Andrew. Yeah, Marco is there. Well, I was looking at him, so it's going to be Andrew's statement. Sorry, Marco. Andrews. The Clausius Kelvin. Andrew. So Kelvin's statement said, no process is possible in which sole result is absorption of heat from a reservoir and complete conversion to work. Okay, so that was Kelvin's statement. Clausius' statement was heat does not spontaneously flow from a hot body to a cold body, right? Is that correct? Or did I miss something? Cold to hot, right? Good, you're all awake. Heat would, of course, spontaneously flow from a hot body to a cold body, right? That's what heat does. That's the spontaneous direction. The other direction, which is not possible. So heat does not spontaneously flow from a cold body to a hot body, and henceforth to be known as Andrew's statement is that entropy of the universe, and universe sounds fancy, but what do I mean by universe? Really, all I mean is an isolated system. Hey, Zoom people, can you hear me? Can you send like a chat box message if you can hear me? Last two times I don't see any chat message. I assume. Oh yeah, I saw something. Good, they can hear me. Wonderful. Last few times the audio was bad. Now, that doesn't mean that every time all of you should just start coming on Zoom, okay? Because I will miss you here. So please come to class. Entropy of the universe, the isolated system, increases in the course of spontaneous change. Has anyone here heard the name of free energy in your Gen Chem or things like that? Rather, is there anyone who has not heard the term free energy ever? Good. So what we will see later is that this Andrew statement, your name's gonna come up every time now. Okay. If you want to change it, we can go to Marco or something else. So it's this statement that the entropy of the universe increases in the process of a spontaneous change. It's for the universe, right? Anytime you're constructing a chemistry experiment, you don't want to really worry about everything else. You just want to worry about your system. And the concept of free energy is a direct consequence of this statement. Later, we will see that free energy of a system is basically related to the entropy of the system under certain specific conditions. That's going to happen after the midterm. For now, we have these three statements. And we would like to show that these three statements are equivalent, that they are all capturing the same, there is nothing new in them. Each of them carries the same information as the other one. In order to do that, the first thing we need to do is to define entropy, S. And we want it to be a state function so that it's not clumsy. You know, once we specify the state of a function, we know what is the entropy. We don't want it to be a path function. So we can manipulate it in nice different ways. And last time we saw the molecular definition of entropy, and we are not really going to use it in this semester, but you will use it in 482, and it's good to be aware of it, where you have Boltzmann constant and log to the base E of the number of ways of arranging a system, the multiplicity of a system. And last time I gave you intuition as to why it is log. Some of you asked whether it's natural log or log to the base 10. I don't really care, because that is all just absorbed in the proportionality constant, right? You change the value. If you change a unit, you can change log. So we don't care about the log that much. And in general, in chemistry, in physical chemistry, you will find people using log without specifying the base. If that has been done, you can assume it is log to the natural base. It's not true in other aspects of chemistry, but in physics and physical chemistry and chemical physics, it's quite true. So we had the molecular definition, which is great, which came around 1905 from Boltzmann, but there is a classical definition of entropy, and that's what we are going to talk about, and that's what we are going to use through the course of this semester. So classical definition of entropy is also, in a sense, related to the fact that entropy involves change in randomness, right? That's how we introduced the second law, that things like to become, on their own, things like to become more disordered, right? On their own, things don't become ordered. So out of all the nice state functions and the ugly path functions we have studied so far, which is internal energy U, enthalpy H, W work, heat Q, which one of these is associated with randomness? Huh? Q. U is the internal energy. Everything has contributions coming from randomness, right? That is the idea of the first law of thermodynamics, that internal energy cannot distinguish whether it's coming from W or from Q. But Q was the random motion. Q was the contribution of internal energy coming from random motion in the surrounding, while W was contribution coming from organized motion, while Q was coming from random motion. So if indeed entropy is something that changes, increases through the course of time, if it is something that increases with randomness, which of these state functions do we think should play a role in entropy? It should be Q, right? Because that one corresponds with S. So let's try to define such a classical entropy. One way to do it would be to say, let's say entropy is equal to Q, delta Q, the heat given to a system. Will this do the job? Well, it is true that as you give more heat to a system, the entropy of the randomness of the system will probably increase, right? But what is wrong with this definition? Why don't, yeah, go ahead. Huh? It will be a path function, right? This delta Q is a path function. There is a problem with it. We want this entropy to be a state function. So if we just did delta Q, we will have a problem. There is one more problem. We are not specifying whether this is heat given to the system during a reversible process or an irreversible process, right? So one way to do it would be to think about delta Q, or to think about delta Q reversible. Let's say you have to go from point A to point B, and you do it in such, and this is some pressure temperature or pressure volume profile. You could take a reversible path, or you could take an irreversible path, right? If you take an irreversible path, then you are in even deeper trouble, because you don't even know what is the pressure of the system, right? Nothing is in equilibrium. So let's make our life easier. So basically, let's write down all our options. Delta Q in general, really, really bad, okay? It could be irreversible, it could depend on path, it will just be complicated. Delta Q reversible, maybe, okay? The frown has lifted up a little bit. Delta Q reversible is still a path function. It is not a state function. So what can we do to make it a state function? Any ideas? Go ahead. That's one way. That's correct. And we know how to do that. If we add delta W, it becomes another state function, right? But that's not randomness. That changes everything. No, it's actually quite interesting. If you divide delta Q reversible by temperature, it becomes a state function. Isn't that amazing? I think it's highly non-trivial as to why this would happen. So you are going along a path from A to B, and you calculate all the heat that you are given to this system along this path, okay? Go reversibly, go in a gradual manner, everything is in equilibrium. Let's call this one as delta Q1. Now take another path, and let's call this as delta Q2. Now take a third path, let's call this as delta Q3. Delta Q1 not equal to delta Q2, not equal to delta Q3 in general, right? There is no reason for us to expect that the heat given along these three paths, even though they are reversible, this is not true. But over the course of the next week or so, we will show that the integral of dq divided by temperature is independent of path. You can take whichever path you want if it is a reversible path, and if along the path you divide by the temperature, you get a state function. And this turns out to be a definition of entropy that is consistent with the molecular definition. I will post some advanced material on this that you can go through. It's a bit messy, it's a lot of math, and it takes like 2 lectures to go through it, but it completes the picture. So we have defined entropy this way. You have a question? Yeah, I mean, depending on what you are keeping constant and things like that, entropy changes in a different way. And that's when we start thinking about why is this a state function, those are the type of arguments we will make. So depending on what you are keeping constant, it will take simpler values, sometimes it will take complicated values. So we just defined entropy. We didn't really define entropy. We defined change in entropy through its change, through its exact differential, such that ds is equal to delta Q reversible, because delta Q reversible will depend on path. But turns out if you divide by temperature, it does not depend on path. This is path independent. We are later going to prove this. It's amazing that it is path independent. It's highly non-trivial that it turns out to be path independent. Just like one of you mentioned, one way to make it path independent was to add delta W to it, right? And then it becomes path independent. But then it is no longer consistent with something that increases with randomness. This has all the nice properties. So and with this, we can classify our different type of changes. We can also talk about delta S during a big, this is for a differential change. This is for a small change, right? If you have a big change happening, then you will integrate delta Q reversible by temperature. And here I don't have to specify which path to integrate over, because I'm making the claim that this is path independent. So you might have a certain path happening. You could go and construct some other path. It's really up to you how you calculate the entropy change. So this is path independent claim. We will prove later, probably next week. So now we can write down that delta S system plus surrounding is positive for a spontaneous change. Delta S system plus surrounding negative means reverse process or the opposite process is spontaneous, not the forward process, but the opposite one. What you were thinking is spontaneous is actually not spontaneous. But if you change it, like you can think of a chemical reaction, right? A going to B. If delta S, and this is happening in some environment, what about delta S system plus surrounding equal to 0? In this case, the forward process and the backward process both are spontaneous. And turns out this is true for any reversible process. So this reversible thing that we have been talking about, where the external pressure is the same as the internal pressure of the gas, or temperature is the same, that one also tends to have, that one also has, not tends to have, always has delta S system plus surrounding equal to 0. Go ahead. Here? No, there is no dt because we are not differentiating. We are taking a differential and dividing it by the temperature at which you calculated that differential. So there is no, so this is good point. This is not dt. If you did dt, then it's not an integral, right? Then it will be d something by d. Then it's not an integral. Integral, you can have only one d. So let's try to calculate this delta S using a very simple example and see how it actually works. And this will kind of remove the mystery of this formula, hopefully. So let's consider a perfect gas, so an ideal gas, undergoing reversible isothermal. So these are, every word carries a very, very specific meaning now, and you are all professionals now. You know exactly what meaning does every term carry. Perfect gas undergoing reversible isothermal expansion from volume VI to VF. So you have a container in which there is a perfect gas, and this container is gradually being expanded, and it is being expanded so slowly that the pressure that you are applying in order to expand it is always same as the pressure of the ideal gas inside. Should this be a spontaneous process or a non-spontaneous process or a reversible process? Any idea? Let's try to develop some intuition. Who said they would rather do logically? You said, right? Instead of math. So you tell me. Use your logic to tell me. Yeah. Yeah, so they would prefer it. The ideal gas should prefer it. If it's a non-ideal gas, then it becomes complicated, right? Because non-ideal gas, the molecules have a preferred distance at which they like to hang out. For an ideal gas, you will see this is spontaneous. They like to go in this direction. So let's, now that was the logical answer, but there is a bit more math here that you will see. This problem math is a bit better, perhaps. So let's try to calculate it. We have to calculate delta S, and we have to go from some initial state to some final state and do delta Q reversible divided by temperature. And we know this is a reversible process, so that's great. We have delta Q reversible here. So now let's try to calculate delta Q reversible. What formula should we start with? Think of this as a problem. This is actually a good practice problem for your midterm. You won't be doing entropy in your midterm, but work with me through this one, and it's good practice. So tell me.
So is it isothermal system 0?
Why? Is that always true?
Yeah.
No.
No.
For a perfect gas, delta U is equal to 0.
Okay.
Remember, you asked me this question a few weeks ago. Come on, Andrew. It was you. So, yeah, so let's start. So the first thing should be first law thermodynamics, okay? Anything you have, start with first law thermodynamics. Don't even think about it. Just write it down and stare at it, and things will follow. I'm not kidding. This is how it goes. Delta U is equal to delta Q plus delta W. So isothermal process. What does isothermal process tell us anything about any of these three quantities? Does isothermal tell us anything about W? No, that's had nothing to do with W. Does isothermal tell us something about Q? Does isothermal mean delta Q is equal to 0? Anyone who thinks that? Let's dispel those thoughts from your head if you think that, okay? A lot of students tend to think that isothermal is no heat being given to us. It kind of sounds like that, right? Isothermal. What is the name for a process in which no heat is being given to a system? Adiabatic, right? It's just a separate name. How about delta U? Does isothermal always mean that delta U is equal to 0? No, for an ideal gas it does. And thankfully, we do have a perfect gas over here. Ideal gas, delta U is equal to 0. Therefore, delta Q is equal to minus delta W. And I'm going to write this as I to F delta Q by temperature because we have reversible process going on, right? So I'm not going to drag reversible everywhere because we know this is a reversible process that is happening. So I'm going to get that out of the way. So we know delta Q is equal to delta W because delta U is equal to 0. What can we say about delta W now? Let's go to next page. So far we have 0 is equal to delta U is equal to delta Q plus delta W. Therefore, delta Q is equal to minus delta W. So what can we say about delta W now? This is an expansion process. Go ahead. Yeah. So this is reversible. So first of all, we have one negative hanging out and we have another negative inside, right? So this becomes plus, and it's a reversible process. So pressure external can be replaced by pressure. What should we do now? So we have delta Q is equal to plus integral PdV, but we don't really want the delta Q for the whole process, right? We have to integrate. Remember, in our formula, we need delta Q, the small thing. So this can be written as delta Q is equal to plus PdV. Okay. And this equation number 1 says that, I will write it down. Well, some of you are on Zoom, so I won't do that today. I will. So delta S is integral of delta Q divided by T. And we just showed that delta Q for this one, for this isothermal expansion of a perfect gas is PdV. Therefore, 1 plus 2 imply delta Q by temperature is equal to PdV by temperature, or delta S is equal to delta Q by temperature. And remember, I ignored the reversible in this formula over here because I know this process is reversible. Otherwise, you will have to worry about that. Is equal to integral PdV by T. What can we do now? Any ideas? Should we? It's isothermal, so we can take out the T. But is that what we should really do? Go ahead. Yeah, so if we took out the T, it actually won't help us because we will be left with PdV and we can't integrate it, right? So let's take out the T in a different way. Let's use the equation of state because it's an ideal gas. So this is going to be nRT by V because pressure times volume is equal to nRT divided by temperature. So we took out the T not by taking it outside, but just simply canceling it out. And this becomes nR dV by V going from Vi to Vf. Therefore, delta S is equal to plus nR natural log of Vf by Vi. Does this follow your intuition? Why? Is this positive? You said it should be a spontaneous process, right? For a spontaneous process, delta S should go up. Is that the case here? Vf is more than Vi, right? So this is indeed positive. We got it correct. Now, one interesting thing to note here is that for an ideal gas, the molecular formula that we saw earlier, this kind of reminds us of that, right? It's the same gas constant, it's just Boltzmann constant multiplied by the number of moles. It's got the same logarithmic dependence, which is very interesting. So it's almost telling us that for an ideal gas, ln W is similar to ln volume, which makes sense, right? The number of ways of arranging ideal gas particles is basically how much volume you have. So it kind of intuitively makes sense. There's nothing profound here, but I'm just trying to draw parallels. So any questions about this? No questions? Okay, good. However, if any of you are really paying attention, I just made a mistake. I used this equation to conclude that this is a spontaneous process. Why is that a mistake? Go ahead. I only considered the system. I just told you that a spontaneous process has system plus surrounding. What I did over here is the delta S of the gas or the delta S of the system. I have not calculated delta S of the surrounding. So actually, using math, I have not been able to prove that this is a spontaneous process yet. I have seen the entropy of the gas goes up, which makes sense, right? It has more ways to arrange it, so that goes up. I have not yet been able to prove that this is a spontaneous process. For that, I will have to consider delta S surrounding. And we will be doing that next time. Today, I don't want to do that. But anytime, and this is exactly the point that I was making about using second law of thermodynamics to deny evolution, for example. If we consider all of us as evolving, clearly our entropy is going down, right? Well, we hope so. We are becoming more and more organized. Everything is, all the cellular structure is coming. So the entropy is going down. How can it be a spontaneous process? But we are ignoring the surroundings, right? So if you take this to conclude that this is a spontaneous process, you're making the same mistake. So on this basis, you cannot conclude whether it's a spontaneous process or a non-spontaneous process. Just like using second law of thermodynamics, you cannot conclude whether evolution is right or wrong. I would like to say I could conclude using second law of thermodynamics that evolution is right, but actually you cannot. You have to consider the surrounding. And I don't know how to calculate the entropy of the surrounding for the evolution problem. So what I would like to do, however, now is to go back to this formula that delta S system plus delta S surrounding is more than 0 for spontaneous process. This was our third statement of the second law of thermodynamics. What I want to show is that this is consistent with Kelvin's statement. What did Kelvin's statement is this? And then we will stop a bit early today because you all have an exam. Is this consistent with Kelvin's statement? What was Kelvin's statement? Kelvin's statement was that you have a hot source. And from this hot source, you are taking some heat to run a motor and you are getting some work out of it, right? And no heat is, and if you don't have any heat being lost from this, no heat lost. If you have no heat being lost from this, Kelvin says this is not possible. Second law of thermodynamics cannot allow this to happen. You should always have heat loss. So what we want to show that if indeed you had such a process in which no heat was being lost, it would amount to entropy of the system and the surrounding being negative. So they are consistent. Okay, so let's show that for this process, delta S system plus surrounding is negative. So we have to define our system and surrounding. So in this case, we call all of this as we consider all of this as an insulated system, not talking to the rest of the universe. Okay, so this whole thing is our system plus surrounding. So we have a heat source. From the heat source, some heat is being lost. right? So be careful with the sign here. This is going to confuse a little bit related to the first of thermodynamics, but I will be careful in how I define things. So this heat source is losing some heat, right? So if you focus on the heat source, delta Q is 0. It was taken away from it at some temperature T. For over here, what is delta Q? Here, there is no heat. Heat change is equal to 0 because everything is going into work. So if we calculate the delta S total for the system, that is going to be delta Q for the heat source up there divided by its temperature. And that delta Q is negative. And temperature is always positive. We know that in Kelvin units. So this thing is negative. So through this argument here, we showed that violation of Kelvin implies total entropy goes down. So both of them are consistent, right? If one of them happened, okay. If we had to be very mathematically rigorous, we should go the other way also, right? I'm not going to do that. I'm just trying to give you some intuition here that if Kelvin was wrong, then the second law, then the third statement, Andrew's statement, I want a name for it also because third statement of the second law of thermodynamics sounds kind of trippy, right? It's like, what? So Andrew's statement would also be violated. You would have delta S being negative. That's why Kelvin and this other statement are consistent. Make sense? Any confusion? Okay. Now let's try to do the same thing with Clausius statement. How do we draw Clausius statement? Clausius statement says, and again, we will think in terms of violation. So mathematically, we are thinking about, how you show things like proof by contradiction. So we are violating the statement and see that violation of one statement leads to a violation of the other statement. That's how we are showing it. So in Clausius, we have a hot body at temperature T1, and we have a cold body at temperature T2, and we have some heat flow happening from the cold body to the hot body. So it's a heat flow, some positive amount of heat is being sucked out from the cold body to the hot body. Okay, so it's like in winter, it's minus 20 degrees Celsius outside, and you could have a magical AC or a heater which simply sucks the heat out of the outside and gives it to you and keeps you even warmer and warmer. It doesn't happen that way, right? Heat always goes out. So this is the violation, and we want to show using this violation, once again, the total entropy of the system becomes negative. So here also we define our system plus surrounding as this thing. And let's try to work through it. How do we, so this full thing is isolated. So how do we calculate delta S total here? What is the delta S total coming from the bottom part, the cold part? Use the delta Q by temperature formula. How much should it be? Let's go with the hot part. The hot part is gaining heat, right? So what is the delta Q for the hot part? It is, yeah, go ahead. It's positive, right? So it is plus delta Q divided by T1. Okay, but the bottom part has lost heat. So the entropy change of the bottom part is minus delta Q by T2. So if you look at this thing, this is plus delta Q multiplied by 1 by T1 minus 1 by T2. And what do we know here? T1 is more than T2. Therefore, 1 by T1 is less than 1 by T2. Therefore, 1 by T1 minus 1 by T2 is negative. Therefore, delta S total is negative. So once again, we lead to a violation. The entropy of the full thing, system plus surrounding. And here we have carefully defined what we mean by system plus surrounding by thermally insulating the full thing. So the Clausius statement is therefore also consistent with the third statement that the entropy of an isolated system during a spontaneous change must increase. So I'm going to stop here and just give you a roadmap for what we are going to do next. so far, what have I done? I have shown you the statements of the second law of thermodynamics. I defined the quantity entropy. I gave you intuition, hopefully, that entropy is related to increase of randomness. And heat is, we think, that quantifies randomness. So we want it to be related to heat, but it is a state function. So heat itself is not a state function. Turns out that heat divided by temperature is always a state function if the heat is being given reversibly. We haven't proven this yet, that this S is indeed a state function. Next, after the exam on Wednesday, we are going to gradually work through proving that S is a state function. The way we have defined it, it follows this property. We are going to do it through an example. This example will be related to the figure that you saw in practice problem 4, where you had a bunch of different curves, right? And some were going like this, some were going like this. We will work over this set of curves and calculate delta S for different paths. So you will get a lot of practice in calculating delta S. And we will show that all these different paths have the same delta S. That's not a proof, that's an illustration, right? That for these different paths, it is indeed. So this will be an illustration that indeed different paths, 1, 2, 3, have the same delta S. That's not a proof. In order to prove it, we will be using something called a Carnot cycle. And that will take us at least 1 or 2 lectures. And using that, we will actually rigorously prove that entropy change as defined, or let me write it this way, that delta Q reversible by temperature does not have to be written as delta S. It can be written as ds. This is a state function. This is what we will work on. So good luck on your midterm. Don't panic. It's not hard. Work through problems. Try everything. Please, please, please do not submit without trying every problem. Okay, please try. Please help me help you. Okay, and good luck.